Good evening. Welcome to what is now our fifth installment of the Frontiers of Cosmology lectures. We held the very first event last year on this same day, coinciding with our graduation day for our undergraduates. We are amazed by the enthusiastic turnout, so thank you for coming. Before we get into tonight's lecture, I have one announcement. A purse was found in the women's restroom. If that is yours, you can talk to our staff in the back to claim it. So tonight's event is sponsored by a new and unique type of center that has been established at UC Riverside. We call it CESI, which is an acronym for the Center for Experimental Cosmology and Instrumentation. It is led as its inaugural director by Professor Barish. Many of you who were here earlier today heard from him, and we'll hear from him again in just a few minutes. He is a Nobel laureate. He was one of the original builders of the LIGO scientific collaboration that detected the first direct detection of gravitational waves produced by two colliding black holes in the distant universe. That won the Nobel Prize in Physics in 2017. And he subsequently was awarded the National Medal of Science by President Joe Biden 3 years ago. So this new center that we're aiming to get off the ground is aiming to develop new innovative technologies in detector science that can enable the next breakthroughs across every field of cosmology. So that includes gravitational waves, the cosmic microwave background, and astroparticle and neutrino physics. And so we ask if you're in a position to be able to do so. We're in the fundraising phase for this new center now. And so if you are inclined to make a donation to the center, you can scan this QR code. And we appreciate any amount for anyone who's able to contribute. This goes directly to supporting students, postdoctoral researchers, and enabling us to keep putting on events like this for free to the public. So I would like to introduce now Dean Peter Atkinson, the Dean of UC Riverside's College of Natural and Agricultural Sciences. Let's please welcome Peter.
Thanks. Well, wow, welcome. Welcome on behalf of a fantastic physics and astronomy department. Welcome on behalf of the college. This crowd speaks to the interest, the deep interest in this subject here in Riverside, and I really do thank you all for coming. Ever since recorded history in ancient Western, Eastern civilizations, there's always been this curiosity, this drive to understand how nature works, what is the basis of everything around us, including our fellow citizens, our fellow species, and everything else, the earth, the water, the stars. And as a geneticist, I could say, in a sort of a comical way, that's in our DNA. It's part of us, that drive, that curiosity. And it always will be so, because science matters, and that drive will never disappear from us. We will consistently, as civilizations, be asking these questions, looking for answers, getting things wrong, then getting things right, and making the world a better place. Science matters. Thank you so much on behalf of the college for coming tonight. I apologize that I'm in between functions because it's graduation time, so I came from Earth and Planetary Sciences, and I'll be off to Botany and Plant Sciences momentarily. I wish I could stay because personally I'm fascinated by this subject as a citizen and as a fellow scientist. But thank this crowd. My goodness, I mean, this is going to be a fantastic centre once it gets established, and then we'll take the department, the college and the campus along a fantastic path into the future. So without that, I'd like to introduce Barry, who will introduce our speaker. And thanks again on behalf of the college and the department for coming here this afternoon. Thank you.
Thanks. I'll be brief so that we can listen to our speaker today. I have the pleasure to introduce Professor Ramamurti Shankar. He's the Gibbs Professor of Physics at Yale University. Oh, picture. Okay, sorry. I leaned on the screen or the board or something. Anyway, Professor Shankar, like myself, received his PhD from Berkeley, UC Berkeley, so he knows the UC system. He went from there to Harvard for a few years as a Harvard fellow, and then joined the faculty at Yale, where he spent the rest of his career, and he's still at Yale. He is not only a leading theoretical physicist, but especially noted for his wonderful lectures. He's won many awards, but I'll just pick one because I think it's the most significant. He was awarded the Lilienfeld Award from the American Physical Society, which is a kind of unique award. It's an award for physicists, it's from American Physical Society, who have excelled at both research and basically public lecturing. So people have pushed two different frontiers. His award citation was the following: his marvelous presentations of the story of physics through teaching, lecturing, textbooks, and public talks. Today, his title is especially intriguing because it's a quote from a famous American baseball player, Yogi Berra. Yogi Berra is before most of your generation, but was one of the most successful baseball players, but also, I'd say, ambassador for America, for sports, for a lot of things, and had a unique personality. He communicated in a unique way. He communicated profound thoughts with using kind of a turn of the phrase. And so you never knew whether he was talking in a confused manner until you thought about it and you knew that what he said had deeper meanings or different meanings. And in particular, today's speaker has picked out, when you come to a fork in the road, take it. You think about what that means. Anyway, it's a great pleasure to introduce Professor Ramamurti.
Yeah, I've turned it on. Okay. I'm very flattered to be asked to speak on this occasion. I've been here for a few days, met a lot of students, met a lot of people in the Cosmology Center, and I'm so impressed with the group Professor Barish has assembled here to attack the problem from many different directions. Now, people who know what the lectures are about know it's about cosmology. The first question they have for me is, what are you doing here? Because I know that I'm going to talk about quantum mechanics, and everybody thinks quantum mechanics is the study of short distances, and the universe is just the other extreme. So what's the relevance of quantum mechanics? Well, one answer is given officially is that it's the year of the quantum. But it's also the year of the snake, the Chinese calendar. I'm not going to talk about that reptile. So to me, that's not the main point. I think every year should be the year of the quantum because it plays such a big role in so many parts of physics, including cosmology. So I got to explain how that happens in spite of what I said earlier, namely the universe being so big and quantum mechanics being the study of things very small. The answer is that the universe wasn't always that big. In the beginning, just after the Big Bang, it was very tiny, smaller than any particle you can imagine. And at that time, the only way to describe it is using quantum mechanics and quantum field theory. So that was long back, but it's relevant today because what happened in the early stages in the quantum world, the quantum state is a highly dynamic and fluctuating state. And those fluctuations, which are microscopic in scale, got blown up to galactic proportions during a period called inflation. That's the period where the universe expanded exponentially fast, and tiny regions got blown up to huge regions, and these fluctuations now determine where matter is, namely the distribution of galaxies and stars and everything. So that's the first relevance. Other thing is, even if you forget the Big Bang, you need quantum mechanics to understand phenomena today, like the behavior of neutron stars. So neutron star you obtain by taking the atom, throwing out the electrons, which is most of the fluff. Then you go to the nucleus, throw out the proton. You take the neutrons and take enough of them to form a star. Now this object is very, very dense. 1 tablespoon of that is supposed to weigh 30 or 40 tons. So you would think if you make a star out of that material, it'll very soon collapse under its own weight. It doesn't because of another principle in quantum mechanics called the Pauli exclusion principle. That principle says that no two fermions are some kind of particles, and neutrons one of them, no two fermions can do the same thing. They cannot be the same place, they cannot have the same momentum, they cannot have the same attribute. So what happens is, inside a star, if the first neutron is at rest, second cannot be at rest. It has to move a little bit. Third one has to move more than that. Fourth has to move more than that. By the time you get the star, the biggest velocities are very big. And it's the pressure of the momentum of these objects forced by the Pauli principle that keeps the star from collapsing. So quantum mechanics is here to stay. It was there from the beginning. It's now, and it'll be there from now on. Now that I've taken care of my imposter syndrome on why I'm here, I will now start by giving my regular lecture, which is to first thank everybody for coming here. I promise you that when it's your turn to give a lecture, I'll be in the audience. I learned this from Yogi Berra, who said, you got to always reciprocate kindness. And this is what he said. Excuse me. You must go to people's funerals because, where is my expert? How do I go back with this? Here. How do you advance over this one? Okay. Now that's funny, but other things Yogi said are also funny. When he was giving directions to his house, he told the people, you turn left, you turn right, then you come to the fork and you take the fork. And everybody thought it was hilarious. So did I. Till I realized in the middle of the night that it was not a laughing matter. Because this is exactly what particles do at the quantum level. When they come to the fork, they take it. And I'm going to explain to you why that is true. But I told myself, as a serious physicist, you cannot laugh at this particular joke of Yogi's. Then that night, things got worse. I went on the internet, tracked down every one of Yogi's quotations, and found that each one of them represents a fundamental truth in physics. So I cannot laugh at any of Yogi's jokes. If you cannot laugh at Yogi's jokes, there's not much left that's funny. That's why I'm kind of downcast and morose looking person. Okay. That's for me, but you guys also look pretty morose and downcast because I know what you're thinking. You're thinking this guy's going to do some quantum mechanical mumbo jumbo. I won't understand the thing he says, and I'm going to feel bad. I don't need that on a happy day like this. So let me tell you something to cheer you up. Here I have to quote Professor Feynman that Professor Barish quoted. He said, no one understands quantum mechanics. Feynman doesn't, I don't, she doesn't, nobody does. So it's not going to change due to this one lecture, so don't worry about it. So why am I still giving the talk? Because I have a plan. Right now, I'm the only one who doesn't understand quantum mechanics. When I'm finished with you, none of you will understand quantum mechanics. Okay. So when I say I don't understand quantum mechanics, it's not literally true. I mean, I signed my book today to some of you guys, so I know I understand it. What I mean is, I know the mathematics. I know how to do a lot of calculations for atoms and molecules and semiconductors. I don't have an intuitive feeling for quantum mechanics, and nobody does. That's what Feynman is talking about. So we all understand the subject only mathematically. It doesn't correspond to anything in our macroscopic world. In that case, what can I tell you? It turns out even a subject like quantum mechanics, which is very esoteric, makes a few statements whose meanings are as clear to me as they are to you. They're not couched in any jargon. That's true for relativity also. So here's a statement I have about special theory. Nothing goes faster than light. That's a statement, and it means exactly what you think it means. Look around and see anything moving, and you time it, you find the speed, it'll be less than the speed of light. Now, that is a very interesting statement because why should there be a limit to the speed? Why don't you put one speed on top of another speed and then get whatever you want? So here's an example. Suppose you have a plane, and the limit on you're not talking about the speed of light. Let's say you're talking about the speed of sound. And someone says nothing can go faster than sound. So you build a plane that goes at 3/4 the speed of sound. And I get into that plane, and I take a gun, and I fire a bullet toward the front of the plane at 3/4 the speed of sound. And you look at me from outside, what will you see? Well, you'll see some anti-terrorist guys jumping on me and knocking me to the ground. But if you follow the bullet, you'll be going at 1.5 times the speed of sound. So what's to stop you from doing that with light? So this is the next thing you could try to do. Here's a plane. It's going at 3/4 the speed of light. Here's me watching, and that is the bullet coming out at 3/4 the speed of light from the plane. So from the ground, it should be 1.5 times the speed of light. But it doesn't happen. That's where the mathematics comes in and tells you the correct answer is that it's only 24/25 the speed of light. So velocities don't add the way we think. And that's what gets us out of the jam. But velocity means the same thing. And the velocity of light being an upper limit is an interesting physical statement. So even if you don't follow the mathematics of relativity, you can go away saying, here's one thing I understand. Nothing goes faster than light. In fact, Alfred E. Newman said long back, This much I know about the velocity of light. It gets here too early in the morning. So after him, many people have thought about light, but Einstein had the next profound statement that nothing goes faster than light. So are there other statements in other parts of physics? So I'll give you one from thermodynamics. You can start cooling things. You can take a drink, you can put it in the fridge. If it's not cold enough, you can put it in the freezer. If that's not enough, you can put it in a liquid helium. So you can keep on cooling it. So you may think you can cool it indefinitely. But it turns out you cannot cool anything below this magic number, 273 point something. That's also a limit. So these are limits which come from the theory which you may not expect. You may not think that you cannot keep cooling forever. So there are similar things in quantum mechanics which says there are some things you cannot do. What is it? It says particles don't have trajectories between observations. So I'll explain what that means. Suppose you throw a football in a stadium, you see the football being thrown, and you're distracted for a while. Then you look, it's been caught by what's that guy in the front, catches them? Somebody in the front catches the ball. So you didn't see it, but the ball definitely had a definite trajectory from the time it was released to the time it was caught. Because everything has to follow a trajectory. That's our intuitive feeling. Now, this assumption, when applied to the microscopic world, does not work. If you assume particles have trajectories, when you don't observe them, you get into trouble. Trouble meaning you make predictions that don't agree with experiment. Now that is a serious no-no in physics. So we guys are pretty laid back about most things. We don't care how we dress. Our socks don't match. I'm talking about fancy physicists who wear socks. So we don't care about any of that. But if you violate experiment, that's a bad thing. That's not allowed. That's what will happen to you if you think particles have trajectories even when you don't measure them. Now, the football is not a good example because football is constantly being bombarded by air molecules, various particles colliding with it. They know it's there. I'm saying if you take a particle, like an electron, I emit it here with this hand, I know it left me, my hand feels the recoil, and it comes and hit this hand, that feels the recoil. I know it was here, I know it was there. It's reasonable to think it must have gone from here to there in some path. That has to be an interpolating trajectory. That's a very reasonable assumption, but it's wrong. That's what is contradicted by experiment. That's the experiment I want to tell you about. So here's the experiment. It's the famous double-slit experiment. It's what's called a Gedanken experiment or a thought experiment. That means it's a stripped-down version of a real experiment you can do. Now, Einstein was a big fan of Gedanken experiments. Now, all of us are fans of Gedanken experiments because we got no money for real experiments. This is what happens in this thought experiment. On the left side, okay, where is the red dot? Where is my helper? Thank you. Okay, you see that they're not going to let me do any kind of lab because I don't know how to handle anything. So I always have my friends supporting me. So here is the source of electrons, like a cathode ray tube. This was long before you guys were born. There are things called cathode ray tubes that emit electrons. So this emits electrons. And it emits them at a fixed momentum or fixed velocity. Then this is the emitting machine. Here is an electron detector. You're seeing the experiment from the top. This is a view from the top. You're looking down, you see the emitter, and you see the detector. Between the two is an impermeable barrier with two slits in it, S1 and S2. That's all you need for this experiment. Electrons will be emitted here. They'll be detected there. And I can move the detector wherever I want, but I'll just pick one location for a while. So I block one slit. I block this slit, I open that slit, and I do a count of electrons coming at the back screen. This X, every X is an electron coming there. Then I do a histogram by moving the detector, and I connect the dots, and I get this curve. Fairly dull and featureless curve. It says most of the electrons will probably be in front of the hole, but they are also on the side. Now you can repeat the experiment with the other slit, and you will get a similar pattern slightly shifted. Now is the crunch. I'm going to open both the slits, and I'm going to tell you to go to place marked X with your detector. And 5 electrons per second used to come here with one slit open, and 5 used to come with both slits open. The question is, what do you expect when, 5 with S1 open, 5 with S2 open, and you want to know what happens when both are open at this particular point I've chosen. If you haven't read the book or if you haven't seen the movie, what answer will you get? You will say 5 plus 5 is 10, so with 2 slits, I should get 10. That is inescapable in classical mechanics because electrons will take either one path or another path, and for electrons planning to go this way, it doesn't matter if the second slit is open. They don't even know there's a second slit. Similarly, those going this way are not affected by the first slit, so they'll carry on as usual, and with both open, you should get 5 plus 5. That is inescapable if you believe in trajectories for electrons. But if you go to this particular point I mentioned and you do the experiment, you will find no electrons come here. So this is a place that used to have 5 on each, but with both open, you get nothing. So that is the end of Newtonian physics. That is the failure of physics, Newtonian physics, staring at you. This is one simple diagram that tells you what is weird in the quantum world. In a quantum world, 5 plus 5 is not 10. If you have 5 electrons coming with one hole, 5 with the other one, you open both, you get 0. That doesn't happen in daily life. For example, if this is a mosquito net and you're sleeping and there's a hole in the mosquito net and here you are, you don't want to be bitten, you don't go make a second hole, right? That's because mosquitoes come in positive integer numbers. There's no way to cancel the mosquitoes. Doesn't happen with particles, but happens with electrons. So that is it. You have to think about this. If you have this, you know that you have to give up on Newtonian mechanics. You have to give up on trajectories. If you believe in trajectories, which I've shown here, the conclusion of 5 plus 5 equals 10 is unavoidable. So when you close a slit, when both these are open, there's no electrons here. If you close a slit, you start getting electrons. So if this is not you, if it's not electrons, if it was you, for example, this is a wall where they tied you up, given you your cigar, and they're shooting bullets at you through this wall. And with both holes open, let us say nothing is hitting you. Somebody wants to help you by closing one hole. That person is not a friend because with one hole closed, you will get some electrons where you got some bullets where you got nothing before. That is the difference between the microscopic and macroscopic world. So now you continue the experiment. I told you to pick one spot named X where nothing comes, but suppose you move the detector up and down and you plot it, you get this oscillatory pattern. Now that's a very familiar pattern. You've all seen that when we study waves. So here is how they enter the theory of waves. So here is another top view. We're looking at it from the top. This guy is now emitting waves. It's a plunger plunging into the water and vibrating. It sends out waves. Waves should normally look like this, but if you go far from the center, they will look like parallel lines. Red means up, blue means down, and everything in between. In other words, if you put your eye at the water level and look, some places it'll be up, some places it'll be down compared to the usual unperturbed level. You see that? I'm going to show it to you again because it took me a long time to manufacture this slide. Yeah. The waves are coming, they're going to hit the slit, they'll come out here, and this will become a source, and it'll go and do something here. Similarly, if you open the other slit, I forgot, this is my detector. Detector, not the kind that Barry and friends built. This is a very simple detector where you take a shish kebab stick, put a little cork in it. The cork can vibrate up and down, and the water goes by, it vibrates up and down. That's the detector of waves. So when waves go past this point, the amount by which it oscillates is a measure of how strong the wave is. And the intensity is another technical definition. It's the square of the height of the wave at each point. Because the height itself can be positive or negative, but the square will be positive. So in an area where the waves are very strong, intensity will be very large. Now you do the experiment with this slit blocked and that slit open, the same pattern you find on the wall. If you open both of them become sources of light, of waves, and the waves will come in, and now if you measure it here, you will find this oscillating pattern. Now it's not a mystery that with two slits open, you don't get anything here. Whereas with one slit open, you got something there. The reason is that the two slits are not sending something which is positive or integer. It's telling the water whether to go up or to go down and by how much. Therefore, the two slits can send conflicting signals to this point, and they can send synchronous signals to this point. Therefore, here the up will add with up and give you a big up, and then soon the down will come and make it go down a lot. Here, whenever an up from here comes, a down from here will come, cancel it. So with waves, you have the opportunity of understanding why, if you open two slits, you get less than with one. So the waves know that there are two slits. That's the whole point. The particle doesn't know how many slits there are. It goes through only one slit. So it'll keep doing what it does with the other slit open or not. But waves are extended, and they go all the way from here to here. If you got two slits, they will do this. That's the whole point. Now here's a more detailed explanation of what happens. One wave starts here, and it's the trough and a crest and a trough and a crest. If you go here, it starts that way, but by the time they come here, they're exactly out of sync. But this is half a wavelength longer than that. The red will come with the blue and cancel it, then a blue will join the red and cancel it. So this is why you get nothing here. So the thing with waves is we have no trouble understanding this pattern. With waves, there is no paradox that if you open a second slit, you don't get any action at one place because the two slits can cancel each other, but not with particles. So you go back to electrons. So in electrons, if both slits are open, you get this wiggly pattern. That's an experimental fact. So what is the property of this pattern is the way in which it oscillates from one point to another. And in wave theory, if you give me the wavelength of light coming from here or water coming from here, and you tell me the distance between the slits and the distance to the screen, I will tell you what this pattern is. So if you want to reproduce the electron experiment, then you must pick a wavelength that is related to the electron's momentum by this formula. H is some constant called Planck's constant. It's 10 to the minus 34. But you might say 10 to the minus 34 what? Don't you know you got to write the units to get full credit? First of all, I have tenure and I don't have to listen to anybody. Secondly, 10 to the minus 34 is such a small number. Who cares what it is, right? Or take 10 to the plus 34. If you got 10 to the plus 34 units of money, yen, dollar, doesn't matter. You don't have to worry about me. So 10 to the minus 34 means very small. So we don't need the units, but that is why you don't see these effects in the macroscopic world. In the microscopic world, if you plug in this formula for the momentum of the incoming electron, you can get this pattern. So we have found a way to reproduce this pattern, but we are not fully happy with this resolution because this is a pattern involving waves, but what's arriving at the detector is not a wave. It's a particle, definitely. So if you sit here, it will hit only one detector. For every trial of emitted particle, you'll get only one detector that's activated. So what arrives is a particle, but the distribution is that of a wave of that wavelength. That's what electrons do. So we don't have to like it. No one tells you to like what you hear, you just have to learn it. So this is what electrons do. They form an interference pattern with the wavelength given by their momentum and this constant. So there's another way to do this thing using Feynman's approach. In Feynman's approach, you don't do waves, you do the following. For that, you have to first learn how to add arrows. So suppose I start in a camp and I go 3 miles to east one day and 3 miles east the next day, you know I've gone altogether 6 miles. Now, if I don't tell you that I don't go horizontally, but I go at an angle, then the distance I've gone is from here to here. So it's clear that the way to add the distance I've traveled is to go from the beginning of the first arrow to the end of the second arrow. That's the way you add arrows. Now, if the two arrows are opposite, they will cancel each other. So here is how Feynman tells you to reproduce this graph. You draw any path you want. This path goes like this. This path goes like this. Along each path, as the particle travels, imagine it has a clock. And the hands of the clock turn clockwise or anti-clockwise, depending on whether this path is longer or shorter than this. So when the two paths come here, what did I do? Come over here. I turned the whole thing off. Yes. So how do you move this thing? Slide. These, this, and this. Okay, thank you. All right. Anyway, if you don't follow my lecture, it's okay. I didn't follow everything she told me, so it's all right. So here it is, how to add arrows. So the point is, when you go on two different paths, the clocks carried by these particles turn one clockwise and one anti-clockwise by different amounts, and the arrows can be at different angles relative to each other. If they come to the midpoint, the clocks have turned by the same amount. They add in parallel. At this angle, one has gone this way, one has gone that way, the net is so much. If you go to this point, one has gone to this 12 o'clock, other has gone to 6 o'clock position, and they cancel. So as you go up and down, they add and cancel, add and cancel. So this is how Feynman's rule works. This is the fork. This is what we mean by saying when particles come to a fork in the road, they take it, because this is two options, and the particle literally takes both the forks. It's a contribution from the two trajectories that gives you the answer you want. So this is what Yogi was trying to tell people. They were busy laughing. They didn't pay attention to what he was saying. Then Feynman had to come and invent this and waste all the time. So if you had paid attention to Yogi, you wouldn't have had these problems. That's the moral of the story here. Now, here's another variation of the experiment. People can say, look, I don't believe that electrons don't go through one slit or another. It's impossible. It has to either take this slit or that slit. So I'm going to put a light bulb here. I'm going to shine light on this, so I will know where the electron went. Then you cannot escape the fact that each electron coming will either go through slit 1 or slit 2. Then the total number must be the sum of these two numbers. There's no room for any cancellation. So you put the light on, and you run the experiment. What you find is a pattern that looks like this. That's a steady, flat thing with no features. And top of that's a slidey oscillation. So what happens is electrons which are seen contribute to the flat, featureless graph, where you just add numbers the way you did in Newtonian mechanics. Electrons which are not seen, have not been observed, they produce the interference pattern. So if you don't observe the electron, you cannot assume it as a trajectory. That's why you can imagine that the answer won't be the simple sum of the two numbers. So when you shine light on it, the answer changes, and that's the property of quantum mechanics, that observation makes a big difference. See, Yogi said this. You can see a lot by just observing. So now I'm going to tell you how we understand this nowadays. How do we live with this experiment? We say that you cannot say is it a particle or a wave. Make up your mind. It's not one of the it's not the dichotomy. It is what it is. So it's a particle in the sense that only one detector will be activated whenever you send an electron from here. It won't hit the whole array of detectors, only one. In that sense, it's a particle. If it hits you in the face, it'll hit you at one point. At that one point, it'll deposit all its energy, all its momentum, all its charge. So what will hit you is a particle, but this graph tells you where it will end up in the double slit experiment. So the role of the graph is the following. If you do this 1,000,000 times and you plotted this wiggly pattern, and you do the 1,000,000 plus 1th attempt, do you know where the electron will go on that final attempt? Answer is you don't know. You can only say that it's more likely to go where the graph is big and impossible to go where it's 0 and unlikely where it's small. So what we've been able to explain with these Feynman lines or with waves is to predict the distribution of probabilities. We never tell you for sure in quantum mechanics where the electron will go. We are now content to simply say what the odds are, or this will happen or that will happen. So that is the okay. Now, here is the difference between probability in quantum mechanics and probability in classical mechanics. We have probability even in classical mechanics. You go to Vegas, you rely on probability, but that probability is very different from quantum probability. So I want to explain to you the difference. Suppose there's a deck of 3 cards. 2 are red and 1 is black. And somebody's shuffling them, and you have to guess what the color will be of the next card. You know there's 2 reds to 1 black, so the black will come up 1/3 of the time, and the red will come 2/3 of the time. That's classical probability. So if you did the 3rd card, these 2 were red, the 3rd one was black, you know the odds were 1/3, but you also know that even before you flipped the 3rd card, it was black. It was not that it turned black during the act of measurement. It was always black, you just didn't know it, and when you open the deck and see, you get the answer. So classical probability gives you the odds of finding something, but something is already doing that even before you measure it. Unlike in the case of electrons, it's not doing anything definite till you measure it. That's the whole point. Electrons don't have any attributes till you measure that attribute. Otherwise, they're in a state of limbo, like going through both slits. So here's probability applied to me. Somebody has studied me for a long time, and this is the distribution of my location. So I'm likely to be at home, likely to be at work, or driving on Route 10. What is smeared here is only the probability. I'm not spared unless I got into a bad accident. I'm at any one location. This is the odds of finding me. But if you found me at this location, you can be sure I was there even before you looked for me. I was not in a state where I could have been anywhere. That's the difference. In classical mechanics, when you have a probability, you get an outcome, the system was doing that thing even before you looked. In quantum mechanics, it's not doing anything particular till you make a measurement, and the measurement tells you what it is doing. So measurement confers a location on the object. Those properties don't exist before measurement. Okay, now we come to qubits. As you know, qubits are bits in a quantum computer, which instead of being 0 or 1, which will be the case here, can be in a state which is neither this nor that. That's the main thing. A classical bit on a computer may have a certain odds of being up or down, but if you caught it at up, it was up even before you looked for it. In the quantum bit, it could be up or down. If you caught it at up, it was not up till you measured it. Till you measured it, it was fully capable of giving either answer. It's that ability to be in this state, superposed state, that's the property of quantum mechanics. That's what's used in a quantum computer. And if you got n bits, they can be doing 2 to the power n things at the same time. And that's what is taken advantage of in doing these computations. Okay, now I'm going to somewhat more esoteric parts of quantum mechanics. So if you didn't follow anything so far, it's going to get worse. So here are 2 particles. I call them Joe and Mo. They are identical. Even their mother cannot tell them apart, but right now I've given them names J and M. They're supposed to go on a date with the girls living across them. Joe is supposed to go here, Mo is supposed to go there. So that's Mo's assignment, Joe's assignment. But suppose the guys decide to do this. Will the dates know that they have changed positions? You and I will know because we saw them doing it. Will the dates know they have? They won't because they look identical, and this person will look identical to either that or that. So when you have 2 identical particles and they have changed positions, in classical mechanics, you know they have changed position. That's the real sense in which they came straight in front or they crossed. In quantum mechanics, when you don't have trajectories, the only thing you know is they were here first and they were here next. You cannot say who came where, because you don't have the interpolating trajectory. Therefore, the final state is not Jm or Mj. Both of them assume too much. You only know there is one particle here and one here. It has no name. So if you block things out, even in classical mechanics, you won't know if they cross, but in quantum mechanics, it's always blocked because if you don't measure it, you don't know who went where. So that's the difference between identical and indistinguishable particles. Identical means if you catch them and look at them, they look the same. Indistinguishable means you don't know who you got. You got one of the 2, and that's all you can say. So these particles, they form 2 families. Some are called bosons and some are called fermions. So here's the deal. If you have a Joe on the left and Mo on the right, you write that state this way. The other way, you describe them this way. The question is, which one should I use to describe these particles? The answer is, you cannot use either one. You don't have any reason to think it's one or the other. You will have to either take the sum or take the difference. This is like saying it comes through slit 1 or slit 2. You don't choose. So bosons are where you do the plus and fermions are where you do the minus. And the minus sign is not supposed to be intuitively clear at all, but it means that if J and M are same, namely they are the same particle, then Jm minus Mj goes to 0, and that's called the Pauli principle. Pauli principle says the 2 particles cannot be in the same state because if you try to put them both in the same state, you get 0. So Yogi said this about the Pauli principle. He knew that there are some places you cannot go twice. So Okay, that's the first quantum revolution. Second quantum revolution has to do with entanglement. That's a tricky concept, even if you're in the business. So I'll tell you what I can or how best to explain it. So two robbers steal 10,000 bucks and run in opposite directions. One is caught with the 6,000 bucks. We know the other has 4,000 even without looking. We know immediately the other has 4,000. How is it contradict anything you know, that if you know what this guy has, you know what that one has, there's no contradiction. That's because the other one always had 4,000. This one always had 6,000 from the beginning, from the time they left the bank. So your measurement does not change anything, just revealed what's going on. But they're quantum particles. The initial state is not 6,000, 4,000, or 4,000, 6,000. It is a usual superposition of these two states. That's how we write it. It's a mixture of two configurations in which one has 6,000, one has 4,000, other where one has 4,000, one has 6,000. You cannot separate them. Suppose you make a measurement and you find out that this guy has 6,000. Then this part of the answer is ruled out, and what remains is only this. So you have to think about what this means. Before you measure this robber here, this one could have been in the combination 4,000, 6,000, or 6,000, 4,000. Each one could have given either answer. But once you measure this one, the second guy is forced to be 4,000. It's not allowed to be a superposition. So the state of the second particle is altered by a measurement done on the first particle. That is called entanglement. Entanglement is a system which is extended in space, but if you do something here, it hurts there. For example, I do this, I start shouting because I'm connected. Now think of the two-body system as one huge connected part. What you do to one part affects the other part, but instantaneously. And people are worried about what that does to Einstein's theory, but we don't have to worry. It turns out it doesn't violate any of the rules. Okay, here are the highlights I want you to carry with you. One, particles can exist in a state which is a sum or over many possibilities of any attribute. It can be many positions at the same time, many momenta at the same time, many orbitals of an atom at the same time. Any attribute need not be unique, could be sum over them. That's the possibility of single particle. If you got two widely separated particles, they can be in an entangled state where a measurement of one of them can affect the state of the other one instantaneously. So this is the end of my talk. So my future plan is to read all of Yogi's statements and try to publish something fast. So last thing I found out was someone asked Yogi what time it was. And he said, "You mean right now?" So I'm trying to see what he meant by that. That's my current project. Okay, thank you.
Uh, what level of research is going to be done at the new building? What level of students? What level of I assume faculty?
Sorry?
What students will be working at the new facility, the new research laboratories?
You have to speak louder. Is the mic on?
Yes. What? Yes, it is.
Yeah.
So like graduate PhD students, they'll be working at the new laboratories.
Yeah.
Okay. Okay.
Did you hear what he said? Yeah, somebody has to tell me what he said. He's too soft-spoken. You heard him? What did he ask? What did he say? To do to understand this, Oh, my program. Oh, that was a joke. I'm not serious. I don't assign to my graduate students the problems from Yogi Berra. I find other places. Any other questions?
Other questions?
What are the consequences or applications of quantum entanglement, if any have been discovered so far?
Entanglement is usually used in quantum computation. In quantum computations, you want to take these qubits and you don't want them to act independently, you want them to act as a unit. So you have to induce an entanglement between them. And then they propagate as an entangled state. That's what you have to do. Oh, there's another hand up there.
What is the largest scale we've ever seen quantum act on?
Quantum what?
Quantum like physics act on versus classical.
Oh, I think my colleague Jack Harris was trying to find how big an oscillator can be and still described by quantum mechanics. Namely, in the quantum oscillator, the energy levels are quantized. In a classical oscillator, they're continuous. So you take a very, very small oscillator, I think a cantilever or something, and you see, as you excite it, how far it can be excited before the levels become continuous. But I don't know what units to use, maybe n equal to 5 or 6 quantum states.
Other questions? Okay, here first and then one in the back.
Sir, do you have any idea when will we reach Q day? That's when all quantum computers will break encryption algorithms.
Do I have any idea? If I had, I would invest heavily right now. I don't know.
Did somebody else have a question? Okay.
What happens if you open up a third slit? Would it just be a different type
Yeah,
of wave?
you will have to, that answer can be obtained from just classical wave theory. Take a partition with 3 slits in it and send a wave of some wavelength, and you can calculate the pattern you will get on the screen. And that will be the same answer for electrons, except you got to plug in the right wavelength depending on the momentum of the electron.
Okay, there's one down here and then on the other side. Could you please pass the microphone?
Are there any ways you've seen quantum physics applied to biology?
Biology. People ask me if quantum mechanics applies to the human brain. And my answer is if the brain is small enough, yes.
Okay. Works for me.
I think there was. Here's someone. Oops, sorry. There's somebody.
You said Joe and Mo were like identical twins, and they were dating other particles that were identical as well, and that's why they couldn't differentiate between those two. What was stopping them from dating each other, and how would that have like reflected in the problem?
That, just repeat the last part. Someone has to tell me what she said. I want to answer that question.
Well, how would it have like changed your conclusion about quantum entanglement?
No, these are not entangled. These are identical but indistinguishable particles. So that, look, I give you 2 particles now, and I throw them towards you. And when you catch them, can you tell me which one you got? In the macroscopic world, you will follow them from my hand to your hands, and you will know whether they came straight or they crossed. The quantum world, when I throw them, you see them. When you catch them, you see them. You don't know what happens in between. So you cannot tell when you catch 2 particles who you got. You can give them names for all you like. The names are not permanent. So giving names to individual particles has no meaning because you cannot track them.
Thank you for the great lecture. What is the most mind-boggling fact about quantum mechanics to you that's still true?
Well, everything is pretty bizarre, right? So I haven't found anything particular that I find amusing, amazing. So that's what I meant by saying we don't understand it. Every part of quantum mechanics is bizarre. After a while, you get used to it. You do a lot of calculations, you think it's business as usual. Only when you give a talk like this, you realize how weird it is. So you don't have to like it, you don't have to love it, you just have to know how to use it.
Other question.
Just for like the quantum entanglement part, if there's like two particles, it's pretty easy to tell. If you get the first state, you can kind of understand the second one. But if there's like multiple entanglements at once, how do you start?
Yeah. You can have entanglement of, yes, you should just follow people in Hollywood. You can entangle any number of people. Yes.
But wouldn't it be harder to start to understand like which like state? Because like there's like multiple spreads and like the money example. How do you even start to like figure out what's what? Because you can't really.
Well, these guys who do quantum computing, they have gates in which you take a qubit and it goes through the gate, comes out entangled, then you can put another one and entangle that. You just let things hang around long enough, they get entangled.
So you use the stream of information to understand which one's what for like the.
I don't know if you can tell who went where in the quantum world. You know, this is what I began with, this is what I ended with. I don't know. I cannot track the trajectories.
Oh, hello. Hi.
Why don't we thank the speaker for a wonderful talk? Okay, only a couple of more questions, please.
I went to a lecture last year, and the presenter said something really interesting to me, that like physics is just like a bunch of fog. What he was studying was like cosmetology, and he was talking about how like even though he's like studied it his whole life, he still doesn't understand it, and there are things like in his lifetime that he's never gonna know. And I guess it's kind of the same for you with quantum physics, how like even though you're studying it, you just have to accept that there are some things that you'll never be able to find out. So I was just wondering how you move through that fog.
I think I'll never be able to understand quantum mechanics at a gut level, if that's what you mean. You can do all the calculations you want, you won't do it. There are other things where you do understand. Sometimes you say, I did the calculation, now let me go back and understand it. That works in the classical world, in which you can understand it. In the quantum world, I don't know anything about. If I say what is really happening, the word expression, what's really happening has no meaning in the quantum world because the language is inadequate.
So for the double slit experiment, right?
Yeah.
You have two slits.
Yeah.
What if you have layers of detectors, right? So write a slit, one layer, and then more distance, more layers, and then so far, so on. If you have enough like layers of detectors, will you be able to figure out the trajectory?
No. So people have tried to beat that problem. It never works. You cannot determine the trajectory without disturbing it. Because when you see the electron, you shine light on it, and the light is carried by photons. And for me, the photon is nothing. I'm standing here, I'm bombarded by a million photons. I take it like a man. But if you go to an electron, you bombard it with a photon, it's a very violent event. That's why measurement has such an impact on microscopic objects.
Thanks for here. Thanks for the really good talk. You also have written a very famous and very good textbook on quantum. What was the motivation on writing a textbook?
Okay, I can answer that. I wrote the book when I was a postdoc for two reasons. First of all, as a postdoc, I felt I wasn't doing anything useful. So I said, let me do the one thing I know I can do, which is write books. Secondly, I wanted to write a book when I still knew what was bothering me. Since then, I've written 3 or 4 more books. My kids give thumbs down on all of them. But they said your first book is good because at that time you knew the student's point of view. That's why I wrote it then. By the way, people told me it's not good for your career to write books. You should not listen to those guys. Because writing books for me didn't take away any time from research. In fact, when I was feeling absolutely awful, I wrote something. Then I said, hey, I'm good for something. I'll go try research again. It's a very good break. Like family, you know, they come in your way, but if they didn't come in your way, you won't get any ideas.
Okay. One final question. This will be the last one.
I was reading about wormholes, and they said that two black holes that are quantum entangled will have a bridge between them.
Yes.
But I was wondering, like, how would you know if the black hole is quantum entangled? Is it even possible to know?
Well, this is the idea that Susskind has been promoting. It's called EPR equals what? What's the other one? ER. That's right, EPR equals ER. So he's saying entanglement between two particles is not that mysterious if they're connected by a wormhole. But you know, I don't know enough about wormholes to tell you anything useful. But obviously they think that's an explanation. It's a testable explanation in some form, but not today.
All right, we'll leave it there with the questions. Let's thank Professor Shankar again.